Look around. From the movement of stars and planets to a bouncing ball, the way water flows, and how light illuminates it all, the universe follows clear and unbreakable laws of nature. We call the laws of matter and energy physics. And when we talk about physics at the atomic scale, we use the term quantum mechanics to describe the physical laws that govern the fundamental behavior of all particles. Physicists have been studying quantum mechanics since the 1920s, and now we're taking a century of knowledge and using it to design new computers.
We picked the science based on what Mother Nature has given us, and then we're continuing to invent or pull in technology from other areas to make our system scale.
Everything around us, deep down, is a quantum system made of tiny particles that comprise atoms. Quantum computers take advantage of nature, manipulate it on a subatomic level to form specific quantum interactions and measure their outcomes. When these interactions are combined through logic, they form what's known as a quantum circuit, which is a program that runs at the quantum mechanical level. Today's computers are fast and powerful. They can do things that previous generations of scientists and inventors couldn't even imagine. This is incredible, but still, there are some problems that classical computers will never be able to solve. They run on computer chips with micro and nanostructures that are so tiny that they are approaching molecular scale. Quantum computers, on the other hand, take advantage of the unique quantum mechanical behavior of atoms and their subatomic particles. It's an entirely new way of thinking about computation, and it's expanding what we know can be achieved using computers. Humanity has been living with digital computers for over 70 years. Every day, at work, at home, and in nearly every aspect of daily life, we rely on computers and their ever-increasing speed, capacity, and flexibility. It's easy to take them for granted. In fact, we came to assume that digital computers can solve any mathematical problem with just enough power and effort. But that's actually not the case. Despite the astonishing advancement of digital computers, there are multiple types of problems that we just think of as impossibly complex. There's an entire class of calculations in computer science and digital computers that remain unsolved. Traditional computers have been sidestepping them by approximation. In other words, they can only get close to the most accurate answer. These are challenges that will continue to grow exponentially in complexity, and they're all around us. Encryption, logistics, financial analysis, medical research, and material design all can benefit from calculations that even the biggest supercomputers can't handle in a reasonable time frame. And those are just a few examples. What if we could use computers to solve the most fascinating and complicated problems in the world while there's still time to benefit from the solutions? We could find correlations between complex parameters, identify the distribution of probabilities, factor impossibly large numbers, optimize complex systems, and solve the problems that are found in the quantum systems that are all around us in nature. Classical computers could get the job done, eventually, but the processing time would take so long that we likely wouldn't be around to find out the answer. Let's take chemistry and the challenge of modeling molecules for material design or pharmaceutical development as an example. To computationally simulate new molecules, you have to calculate the potential interactions between all atoms and their subatomic particles. Consider a single caffeine molecule. To simulate it in a reasonable amount of time, we would need a traditional computer with a semiconducting mass larger than the moon. But quantum computers can simulate molecules effortlessly because they already use atoms and subatomic particles as their underlying building blocks.
The amount of computational power that these quantum computers will have is really just mind-boggling. And it just gets better. Every time you add a qubit, the computational power goes up by a power of 2.
And quantum computers can solve many problems beyond quantum systems in nature, too. Many problems with immense numbers of combinations can be described as quantum problems. Imagine a logistical challenge like optimizing the flow of packages. A global carrier has hundreds of thousands of vehicles delivering packages from anywhere in the world to anywhere else in the world. As each incremental element gets added, the size of the problem multiplies and balloons. Now think about the compounding variables of distribution centers, regional carriers, and individual truck routes. This might seem like something we've already figured out, but we really only approximated the problem. Getting packages from point A to point B is the bare minimum. We can do better. How much savings or potential gains could be realized if each truck could finish its route 5% faster? How much pollution could be avoided if it required 25% fewer trucks? Quantum computers are not meant to replace traditional digital computers, but to augment and accelerate solutions to extremely complicated problems. With quantum computers in our toolkit, we may be able to fight global warming by discovering materials to capture carbon straight out of the air, inventing more effective solar panels and batteries, and making our power grid more efficient and resilient. We may be able to customize medical care, analyze DNA for identifying new treatments, simulate molecules for developing new medications, reduce risk in our financial systems, optimize our overloaded transportation infrastructure, reduce logistical overheads, minimize waste by making better predictions of supply and demand, improve autonomous cars by making them safer and more reliable, and so much more. So, how does it all work anyway? Stay tuned as we dive deeper into how quantum computing is able to achieve this technological feat and the unique ways computation is performed using quantum mechanics.